Hello there. In this video, we're going to continue our discussion on the roots of polynomial functions. In this video, we're going to be primarily focusing on a very special formula known as Descartes' rule of signs, which can tell you how many positive or negative real zeros that this polynomial may have just by only looking at the coefficients of the polynomial. Alright, so before we actually get into stating what Descartes' rule of signs actually says and how to use it, I just want to briefly introduce a couple notations that I'm going to be using throughout this video and also the second part to this discussion. And that is what we call the sine function. Some people also refer to this as the signum function. And this function is defined as follows. So it's abbreviated simply by just SGN. Some people just say the sign. So the sine of a number x is going to be equal to, so it's going to be a piecewise linear function. It's going to be defined to be equal to 1 if the number x is positive. It's going to be defined to be equal to -1 if x is negative, and it's going to be equal to 0 if x is neither positive nor negative. And again, we say this is the sine of x, right? And that's not to be confused with the trigonometric function, sine, related to sine and cosine and stuff like that. So for example, just some basic examples of this. So if I ask you what is the sine of -5, well, since -5 is negative, that's going to be equal to -1. If I ask you what is the sine of 5/3, since that's positive, that's going to be equal to +1. And if I ask you what is the sine or the signum of 0, then you should be able to tell me that that is equal to 0. All right, so with that function defined, let us also define a new term that we're going to use. So definition. So let us suppose that P is a polynomial with coefficients. So usually the coefficients is a sequence of real numbers ranging from 0 to n. So there are n plus 1 coefficients of a degree n polynomial. And more in particular, these coefficients are not equal to 0 for 0, 1, 2, all the way up to n. Therefore, there are going to be no terms missing in this polynomial expression. So you do not have something, for example, like x squared plus 0x minus 6. Like this is a polynomial, but this type of polynomial we're not going to consider because, one of the coefficients is 0. So what we're going to do, so if the sine of coefficient ak is not equal to the sine of the coefficient right next to it, we call this a sign change of polynomial p. So let me do an example to sort of illustrate this idea. So let's assume we have the function phi of x is equal to x cubed minus 2x squared minus 5x plus 1. So here's a polynomial whose coefficients are non-zero. So we're going to look at the sign of consecutive terms, and of course the polynomial needs to be in decreasing order in order for this to be well defined. Alright, so as we see, this coefficient here is positive. This sign here is negative, this sign is negative, and this sign is positive. So the sign of 1 and the sign of -2 are not equal to 0. Therefore, this is a sign change. But if you look from -2 and -5, they have the same value of the sign. So this is not a sign change. But if you look from -5 to 1, they are different signs. Therefore, this is a sign change. So therefore, the function phi has two sign changes. So with this defined, now we have all of the tools to easily express what Descartes' rule of signs actually says. And we're not going to prove it, we're just going to state it. So let us suppose P is a polynomial with K sign changes. So in this example above, we have two sign changes, so K is equal to 2. So the theorem says, Descartes' rule of signs says, then P has exactly K, K minus 2, K minus 4, all the way down to something greater than or equal to 0, positive real zeros. Or K minus 2, K minus 4 possible real zeros. And all of those are exclusive ORs. So that's what Descartes' rule of signs says. And there's also one that talks about the negative real zeros, but we'll illustrate that in the follow-up video to this. So let's consider the function f of x is equal to x cubed minus 2x squared minus 5x plus 1. So let's look at the sign changes here. So we go from positive to negative to negative, that doesn't work, negative to positive, that works. So that means k is equal to 2. So that's how many sign changes that f has. So by Descartes' rule of signs, we have that f has either, so f has either 2 or all multiples of 2 less than this number k. So the only multiple less than 2 of 2 less is going to be 0. Positive real zeros. So it's either got 2 or 1. So this polynomial has degree 3, so by the fundamental theorem of algebra, we know that this polynomial has exactly 3 complex zeros. So Descartes' rule of signs tells us how many positive real zeros that this could possibly have. And it says that either 2 or 0 are going to be positive. So let's just sketch a couple of these scenarios to sort of get an idea of what this could possibly look like. So two positive real zeros is going to look like that. So there's our two positive real zeros. We're not looking at the negative side, keep that in mind. Or it has none. So that means it could look something like this. So this is our two positive real zeros, and this is our 0 real zeros case. Now, one graph that it cannot be is the case where it has one positive real zero. So the graph where it sort of looks like this case is not possible for this particular polynomial. So if there's two sign changes, it's impossible for there to be one positive real zero for that polynomial function, which is a little interesting. So let's look at a polynomial who has another degree higher. So let's look at the function g of x is equal to 3x to the fourth plus 2x cubed minus 5x squared plus 2x minus 1. Now let's count the sign changes for this. So that's positive to positive, so that's not okay. Positive to negative, that's okay. Negative to positive, that's okay. Positive to negative, that's okay too. So we have that the number of sign changes k is going to be equal to 3. So by Descartes' rule of signs, that means G has either 3 or all multiples of 2 less than 3. So the only one that satisfies that is going to be 1 positive real 0. Depends whether it's 3 or 1. So the degree is even, and the leading coefficient is positive. So by the end behavior and the fundamental theorem of calculus, we should know a couple possible scenarios for this. So it's either going to have 3 or 1 positive real 0. So what would a 3 positive real 0 graph look like? So that means it has to have a graph 1, 2, and it has to sort of bounce off that point, right? So there's 1, there's 2, and there's our third, right? So this is our 3 case. And let's graph our 1 case. So 1, 2, so there's our 1 case, right? And there are a couple other scenarios that would also satisfy either 3 or 1 in terms of the graph. You can be creative with this. For example, you can have 1, 2, 3, right? So you have something like that, right? Possible. Now we're not going to really discuss, how multiplicities sort of fit into this picture, but any one of these cases could be the case, right? So what would cases for which it would be not possible, right? So not possible. So you can't have 4 possible positive real zeros, so you can't have something like that. So that's our 4 case. You can't have 2. So 1, 2, that's too many. 1. So that's our 2. There's our 2 case. So you can't have 4, you can't have 2, and you can't have 0, right? So Descartes says it either passes once or 3 times. It can't be 0, 2, or 4. So that's just a basic introduction on Descartes' rule of signs. In the next video, we're going to talk about the other side on how we can sort of look at the negative side of the real values, and also how this can be sort of tagged along with the rational zeros theorem in order to have a very smart way of finding all the possible real zeros for a polynomial function.